A river is 57 meters wide and has parallel banks. Boat B departs from point P on its northern bank and lands at point Q on its southern bank. The actual velocity of the boat is 4I minus 3J meters per second. Now, by actual velocity, we mean the velocity of the boat as seen by a fixed observer on the bank, not by someone in another boat moving with the river. Okay, a person moving with the river would see the boat's velocity as something different. But to a fixed observer on the bank, the boat appears to move at a velocity of 4I minus 3J meters per second. Car C travels due east at a constant speed of 7 meters per second along the southern bank of the river. In the first question, we want to get the velocity of C in terms of I and J. Well, we know the magnitude of this vector. It's 7 units long, where a unit refers to 1 meter per second. We're dealing with units of velocity here. Now here are our fixed axes. Okay, they're not moving with the river, they're fixed on one of the banks. Okay, so the y-axis is pointing to the right, the j-axis is pointing up, so that's why vector VB makes sense. You can see that its j component is negative, it's pointing in the negative j direction, but its I component is positive, it's pointing to the right, plus 4I. So vector VB is made up of two components. One component is 4I and the other component is minus 3j. And by the triangle law we add these to get vector VB. Okay, so nothing new here about the positioning of the axes. Now vector VC, what we're after, is pointing to the right. It has no j component. Okay, so vector VC is equal to 7I. You could write in 0j, but we normally don't do that. I is a unit vector, that is a vector of length 1 pointing to the right. Vector VC is 7 times longer than it. Now I haven't drawn this to scale as you can see, but this vector is meant to be 7 times longer than unit vector I. So to get vector VC we multiply 7 by I to get a vector pointing in the same direction as I but 7 times longer. Next we want the velocity of B relative to C in terms of I and J. So as we've seen in previous videos, we write that as VBC. It means the velocity of B relative to C. So we've got to imagine a set of axes centered at C. So this dot represents the car. Okay, and these axes are moving with the car. We can call them IJ again, but in sometimes I dash and J dash is used to distinguish them, but that's not used here. We just call them a set of IJ axes, but they happen to be moving, whereas this set here is fixed. So we've got to try to imagine what the velocity of the boat will look like as seen from the car. Well, before we use the formula, let's try and get a feel for what's going on. Okay, the car is moving to the right with a speed of 7 meters per second, but notice that the horizontal component of the boat's velocity is 4. Okay, so the boat is moving along this dotted line. Let's see what happens when the boat gets here. Well, we can imagine the projection of this point onto the horizontal, or the positive y-axis. Okay, we project vertically onto the horizontal. The horizontal component has a magnitude of 4, so we will see this projection of the boat moving with a speed of 4 meters per second along the bank. If we can imagine just projecting the boat, or the shadow of the boat if you like, over here. Okay, and we can see that that projection has slower speed than the speed of the car. So we expect the car to overtake the boat. So from the point of view of someone moving in the car, the boat will appear to be moving backwards, to the left. As a matter of fact, without knowing any formulas, we might guess that the boat will appear to be moving to the left with a speed of 3, because 7 minus 4 is 3. Now, as for the vertical component of the boat's velocity, well, that won't change. Okay, if we imagine when the boat is here, projecting it onto a vertical line, okay, this projection will appear to move towards this southern bank with a speed of 3. Okay, this is the speed now, so I'm only just indicating the magnitude. The car's velocity is entirely in the I direction. It has no J component. So as far as a person moving in the car is concerned, the vertical component of the boat's velocity doesn't change. Anyway, let's get back to just using the formula. We saw in the previous video that if we want the velocity of the boat relative to the car, we get the velocity of the boat, VB, and subtract the velocity of the car. So the first letter in the subscript appears first, and the second letter appears second, so it's an easy formula to remember. So by VB we mean the velocity of the boat relative to the fixed axes, and by VC we mean the velocity of the car relative to the fixed axes. The velocity of the car is 7i, so we have to subtract 7i. Putting the I terms together, 4i minus 7i gives us minus 3i, and then the j term is minus 3j. So from the point of view of the car, the boat's velocity looks like this. This is the vector minus 3i minus 3j. To plot that vector, we go to minus 3 on the horizontal axis, and then we go to minus 3 on the vertical axis. So we plot the point with coordinates minus 3, minus 3. We plot that point on the using the moving axes now, not the fixed axes. So because the velocity vector is like this, the boat appears to be moving with a speed of 3 units to the left, and it also appears to be moving down with a speed of 3 units. Well, 3 meters per second. Next we want the magnitude and direction of the velocity of B relative to C. Let's start by getting the magnitude of the velocity of B relative to C. Okay, we can write it like this, or we can write it like this. VBC without an arrow. Two ways to write the magnitude of a vector. Actually, I'll show that vector over here. Now, I tried to show it in here, but it's a bit crowded. So it'll have to point in this direction. You know, we could put our moving axes up here, and the axes are moving in the direction of vector VC, of course. It doesn't matter where we put our moving axes, actually, as long as they're moving with velocity VC, which is 7i. So they have to be just moving to the right with a speed of 7. So to get the magnitude, we're just using Pythagoras' theorem. So I'll show what's going on geometrically as well, just as a reminder. You know, this point is meant to be the origin. Well, we can put our place our velocity vector's tail at the origin. If that's the case, then the head will be at the point with coordinates minus 3, as we already saw, which means that this distance here is 3 and this distance here is 3. So I'm just taking distances now. These are positive quantities. Of course, the coordinates of the point are negative. Okay, and then we just apply Pythagoras' theorem. We want the hypotenuse of this right angle triangle, so we get the sum of the squares of the two short sides. We don't have to worry about putting minus 3 in here, because when we square minus 3 we get plus 9. It doesn't matter. So we end up getting root 9 plus 9, root 18. So the magnitude of this velocity vector is the speed of the boat as seen by the car. The speed of the boat relative to the car. Now we are going to get the direction of this vector in terms of compass directions, north, south, east, west. You know, so this is the horizontal here. This direction is north, of course. This is south. This direction must be west. To get the direction of the velocity, we could either get this angle here, or we could get this angle here. I'll work with this angle. So how do we get this angle? Well, let's call this angle A. So in this right angle triangle, the side opposite A is 3, the side adjacent to A is also 3. So we could use tan A. Well, we could use sin A or cos A if we want, but I'll use tan A. So tan A is opposite over adjacent. That's 3 divided by 3, which is 1. So A is inverse tan of 1, which is 45 degrees. Now, without doing any trigonometry, you might have spotted that this is an isosceles triangle. It's an isosceles right angle triangle, actually. So these two angles must be the same. And they must both add up to 90 degrees, since we're dealing with a right angle triangle. The three angles add up to 180. They both add up to 90, they must be 45 each. So for the direction, we could say south 45 degrees west. That's if we work with this angle here, but we could have worked with this angle out here. Because this one in here is 45 degrees, this one out here must also be 45 degrees. So we could say west 45 degrees south, using that other angle. This one here, they happen to be the same in this situation. So if we use this angle here, we're facing west, but we're veering 45 degrees south. And if we use this first angle, we face south and veer 45 degrees west. So we say south 45 degrees west. Next, we want the time it takes B to cross the river. Now, the quickest way to do this is to consider the vertical component of B's velocity. B starts at point P and it heads towards Q. So let's suppose B is at this position. Well, let's consider the projection of B's position onto the vertical. As we saw before, the vertical component of VB has magnitude 3. So the speed of the projection is 3 meters per second. So basically we have to calculate how long it would take a point moving with a speed of 3 meters per second to travel a distance of 57 meters. Now for constant speed, we just use the formula distance travelled divided by time taken. And we need to just turn this around to get the time taken. So we interchange speed and time. So the time taken is the distance travelled divided by the speed. So this simple formula is true when the speed is constant, as it is in this case. The distance is 57 meters and the speed is 3 meters per second. Working this out, we get 19 seconds. As an aside, notice that the meters cancel out and we have 57 over 3 over s, and if we multiply above and below by s, we get 19s. 19 seconds. Okay, so the time taken for the projection of the boat onto the vertical to go from P to this point here is the same, of course, as the time taken for the boat to go from P to Q. Finally, we want the distance from point P to point Q. Let's consider this right angle triangle here. We have one side of it. That's not enough, of course. We'd need another side, or an angle, another angle apart from the 90-degree angle, in order to fully solve this triangle. We can actually find this angle in here. I'll mark it here in this diagram, because we can find the angle next to it. Okay, these two angles add up to 90 degrees. So I'll call this angle in here A. Actually, I'll call it alpha. I used A in a previous part. Now, in the right angle triangle that contains angle alpha, tan of alpha is the side opposite alpha divided by the side adjacent to alpha. And we have the lengths of those two sides. The length of the side opposite alpha is 3. So we forget the minus sign and just consider the distance. That's a positive quantity. Just the magnitude of this vector is 3. And the magnitude of the adjacent vector is 4. Inverse tan of 3/4 is 36.87 degrees. As a matter of fact, we don't have to find angle alpha at all, although this is one good way to do it. Get angle alpha, take the result from 90 degrees to get this angle in here, and then use some trigonometry to solve this triangle, in particular to get the distance of P to Q. What we do is we notice that this angle up here, alpha, is the same as this angle down here. Now, this pair of z angles, well, this is a pair of z angles. Okay, because this line here is parallel to this line and we get this Z shape formed. Now we look at the big right angle triangle. So I'll mark alpha in here. I could actually work with this one, but I've decided now to work with this angle here. It's a little bit more straightforward. Now, in this right angle triangle, the side opposite alpha is 57. The hypotenuse is what I'm calling x. X is what we want. The sine of alpha is opposite over hypotenuse. Now to get x, we just interchange these two. So x is 57 divided by the sine of alpha. How do we get the sine of alpha without getting alpha? Well, the tan of alpha is 3/4. So what we can do is construct a right angle triangle containing angle alpha. Make the side opposite alpha in the triangle 3. Make the side adjacent to alpha 4. Alpha is some acute angle that is in this problem. Okay, some angle between 0 and 90 degrees, so we can always make this construction. And from it we can get sine alpha. So we don't need to actually get angle alpha. Sine of alpha from this right angle triangle is the side opposite alpha, which is 3, divided by the hypotenuse. How do we get the hypotenuse? Well, we have two sides of this right angle triangle, so we just use Pythagoras. We square the two sides, sum them. 3 squared plus 4 squared is 25. Take the square root to get 5. So that's the famous 3, 4, 5 right angle triangle. We don't even have to calculate it. We see it so often. So we just plug 3/5 in for sine alpha. So we 57 divided by 3/5. That's the same as 57 divided by 3 and multiply by 5. 57 divided by 3 is 19. 19 times 5 is 95. So that's a distance. The distance is in meters.